So here is the section where we learn how to take derivatives of functions that are multiplied or divided by another function. So we saw earlier, we saw an example which asked us to take the derivative of, let's say, 2x plus 1 times, I don't know, x minus 3. So what we do in this case is we FOIL, right? We multiply everything. So it's going to be 2x squared minus 6x plus x minus 3. And then we will take, we'll combine like terms. So that's going to be 2x squared minus 5x minus 3. And then it will be 4x minus 5. So these are this is the way to take the derivative when we have those two polynomials, those two binomials multiplied. But now we're going to say, is there another way? Right? If you try, so let's go this way, wrong. This stuff is wrong. If you try to take this term by term and then multiply the results, you will see that you get the wrong answer. So if you say that this is the same as this, you're wrong. So don't do it. But I have to do it. I hate doing this because I don't want you to remember the wrong thing. But then I have no other way of demonstrating that it's wrong other than do it. So I did it the right way up there. And now what I'm writing in blue is wrong. If you simply take derivatives separately, you will get the wrong answer. You see, the derivative of the first one is 2, and the derivative of the second one is 1, and the answer is 2, but we know it's not 2. You see that? So you are not allowed to take separate derivatives and multiply those. Instead, we are using something that is called the product rule, which is a method to take these derivatives. Now, if we can multiply and do that stuff, why would we learn product rule? Well, that's two polynomials. What will happen if I am to mix in e to the x or mix in sine x? They're not going to multiply with x and x squared to create one single thing. So we have to learn these two formulas, one for multiplication, one for division. So product rule is first. And the product rule says the following thing. If we are trying to find the derivative of f times g, so f and g are functions of x, then we are going to copy f, find the derivative of g, and then copy g and multiply by the derivative of f. So this is the formula that we are going to use if we cannot FOIL. This is the formula that we are going to use even when you can FOIL, because it should be faster than foiling and all that algebra. So let's test it immediately on our previous example, which we solved up there. So we have 2x plus 1 times x minus 3. So what I'm going to do here is I'm going to say that the first one is f, the second one is g, so it's easy for me to follow the formula. So copy the first one, 2x plus 1, times the derivative of the second, which is just 1, plus copy the second, which is x minus 3, times the derivative of the first, of f, which is 2. And now when you solve this, you just clean up the algebra. You have 2x plus 1 plus 2x minus 6, which altogether is 4x minus 5, and that better be the same. Yep, 4x minus 5. So some of you might memorize fg Some of you might memorize the verbal. I don't know, for whatever reason, I'm visual. For me, graphs, charts, give me a lot of that stuff, and it just clicks. For some reason, I remember this as a derivative, copy the first, derivative of the second, plus derivative of the second, copy the first. That's what copy the first, derivative of the second, derivative of the first, copy the second. I remembered it that way for some reason. I don't know why. I usually never do that. But for product rule, I did it. And I also memorized the same way the quotient rule, which is the second part of this lecture. So copy the first, derivative of the second, plus copy the second, derivative of the first. So let's take a look at an example from the textbook. They have a whole bunch of these examples. I just need to get there. There we go. So what is the derivative of x cubed times e to the x? Let's see what you come up with. So let's do it together. Copy the first, x cubed, times derivative of the second, well, that stays e to the x, plus copy the second, which is e to the x, times derivative of the first, 3x squared. Now, the good practice is to factor everything you can and give the answer in the factored form. You are doing this because chapter 4 is coming up. So right now, there is no need to do it, but you are doing it now for a practice and preparation for chapter 4, where you will be setting these things to 0 and applying it, right? So what's common? X squared e to the x is common. From the first one we have x, from the second one we have 3. So that would be the answer in the factored form. So we try to factor every answer and get the simplified form in the factored form. Let's see what else is there. Pretty much they're all the same. So let's see, how about this one? d dx of 3 ln x times square root of x minus 1. So what is the derivative of that? Let's take a look. You want to see? Copy the first, 3 ln x. Derivative of the second, we know that that's, hopefully by now you know it's 1 over 2 root x, because it's 1/2 times x to the negative 1/2. Derivative of negative 1 is 0. And then we copy the second, which is, so plus square root of x minus 1, and then times the 3 ln x. What's the derivative of 3 ln x? 3 over x, yes. So it's 1 over x for ln x, and then times 3, so 3 over x. So what can we factor? The only thing that we can factor here is number 3. So let's factor 3, and we are left with ln x over 2 root x plus root x minus 1 over x. Now you can rationalize, put the root x. That will actually allow us to kick x out as well. Awesome. So let's write one more step because we can. So square root of x ln x divided by 3x, no 2x, sorry, 2x, plus root x minus 1 over x. Now you see that you can kick out 1 over x as well. So it's 3 over x outside. Inside you have square root of x ln x over 2 plus square root of x minus 1. And this would be simplified answer as far as possible. Now, one thing that I don't particularly like about the book we are using is that they are forcing early something is called a chain rule in just one case. They're asking you to memorize the formula that the derivative of e to the ax is ae to the ax. Now, this is actually a chain rule. We're going to cover this in 3.6. But they're asking you to memorize the formula rather than e to the x is e to the x. E to the ax is a e to the ax. And they want you to use this on examples. So let's start a simple one, and then we'll have one with the product rule in it. So how about, what is the derivative of e to the 5x? And the answer is 5e to the 5x. Very good. That's it. So let's take a look at an example where you have this. So 15x times e to the 3x. 15x times e to the 3x. Let's see what you come up with. So, we got it? Copy the first, which is 15x. The derivative of the second is 3e to the 3x. Copy the second, which is e to the 3x, times derivative of the first is just 15. What's common? 15e to the 3x. What's left? 3x plus 1.
Now,
Yes.
when we're pulling out our f's and g's, they have to have x in it, right? I mean, you can't just say f is 15. Right? You know
Well,
what I mean?
it's multiply. Ah, yes. You see, this is
Because that's like 3 terms in there. It's kind of.
it's like 3 functions. Yeah, it could be understood, but 15 is a constant.
Yeah.
Technically, this 15 can actually be kicked in front and not worried about at all by that C rule.
Oh yeah.
It is x and x that create these functions that we will go with f and g. So what I decided to do is to do f and g this way.
Right. Okay. Now with the product rule, we're always dealing with 2 f and g, but is there like another rule when you apply like a third or fourth or?
Yes, there is a triple and quadruple. You can have as many as you want, and they will actually behave like polynomials. Actually, you would have to do the second derivative of the first, and then 2 in between derivatives, and then the second derivative of the last. It's a little bit trickier to do. I don't think that this book actually has that. Do they? No. Yeah, this book doesn't have that. Larson book does. If you open the Larson books, you will find the explanation for it if you're interested. So that would be the product rule. The most important thing to understand is that you are not allowed to take derivative term-wise and then multiply those answers, because clearly what's done here in the blue, that would give you the wrong answer. This is correct answer. So the only right way to do this problem is, if you can foil and then do it, or you are forced to use the product rule formula, which you need to memorize. Now that product rule formula, guys, is going to stay with you throughout education. There's going to be in calculus 2 integration techniques, which would be the backwards formula. Differential equations, there's going to be something called integrating factor, which is going to use this. There's going to be a lot of derivatives that we are going to take in this class, and Calc 2 and Calc 3 are going to use product rule. So this is one of those formulas that you will use very frequently. So the sooner you learn it and get comfortable with it, the better the results. Quotient rule. So now we are dealing with the derivative of f divided by g, where g is not 0. So it's going to be g squared in denominator, and then gf prime minus fg prime. Wow, the air conditioning stopped working and it's not even 30 degrees yet. So that would be the quotient rule. Derivative of the quotient of two functions. That's the formula, just learn it. Now, one student once told me, and I don't know why I memorized this, I never remember this stuff. I told you, the way I remembered product rule was copy the first derivative of the second plus copy the second derivative of the first. I usually don't memorize things that way. Over here, the way I memorize this, because I learned this when I was still getting acquainted with English language, the way I remember this was, I start with g squared. So I say copy the bottom squared, and then I go in the numerator and I say bottom times the derivative of the top minus top times the derivative of the bottom. That's how I remembered, because top and bottom were the words I didn't know numerator and denominator at that point yet. I was struggling with all those terms. So for me, top and bottom were the words that I was using to memorize, and then I just remembered bottom squared, and then I went. And then I explained that in class, as I usually do, just like I did right now. And one student said, oh yeah, there is a formula. It says, there is a song. And he went low d high minus high d low over low squared. So it is, right, top and bottom, and then high and low, right, the top and the bottom. So it's that low d high. D high means derivative of the high, right, of the top. So low d high minus high d low over low squared. Just whatever works for you, all right. Just get that formula down. So we are looking into, let's say, derivative of e to the 3x divided by x squared minus 1, for instance, right? So I always start with denominator and I copy. So Control C, Control V, all right, and then square it. And then you have another Control V over here. You just copy it as is. So this is how you start. You take the denominator, you copy it twice, and you square it in denominator, and then you start thinking about derivatives and things. So derivative in the numerator is going to be 3e to the 3x minus. So 3e to the 3x minus. And then we have e to the 3x, and then the derivative of the denominator is just 2x. Is there anything that we can factor? And the answer is yes, we can factor e to the 3x. So e to the 3x, and the rest stays. So we have 3x squared minus 1 minus 2x, minus 3, divided by x squared minus 1. Please do not FOIL this one. Always leave it in that. That's the factored form. That's the good form. Because when you set this whole thing equal to 0, eventually in chapter 4, 0 is just going to kill that denominator. So we don't care how bad, threatening, or whatever word you want to use it looks like. 0 will always kill it in chapter 4. So don't waste your energy on foiling or anything with the denominators. Just completely ignore them. Whatever they are, they are. It's the numerator that you need to focus on and foil, factor, do whatever you can to make it look nicer so you can easier solve it. So what do we have at the end? We have e to the 3x, open parenthesis, 3x squared minus 2x minus 3, divided by x squared minus 1 squared. And that would be the answer for this question. So let's take a look at some textbook examples from homework, and you guys can do the homework later. So let's go with, wow, these 3 questions are the same. Ooh, here's a really cool question. Look at that. Do you see how you can use both product rule and quotient rule on this one? If you rewrite it, right? What is it? It rewrites as what?
X times 1 over e.
Yeah, so it's either x times e to the minus x or x over e to the positive x. Because that negative on x in exponent pushes this downstairs, becomes positive x. So you can either do the product rule. So how about you do both and get the same answer? Do the product rule, simplify, do the quotient rule, right, when you write it as x over e to the x, then do the quotient rule, and you have to get the same answer because it's the same problem. 2 different ways to do it, but you have to get the same answer at the end. Really cool question. Props to the book. Let's take a look at this problem together. We are going to solve this in two different ways. So first, since it's set up that way, let's do the product rule, which means copy the first one. Derivative of the second one is negative e to the negative x, because we are observing that negative x is negative 1 times x, and then that's that a, negative 1, that goes in front, plus e to the minus x times the derivative of x is just 1, so we'll leave that there. I have negative x e to the negative x plus e to the negative x. Now I'm going to do the algebra here as negative x over e to the positive x plus 1 over e to the x. We have the common denominator already, so we have 1 minus x over e to the x as the answer here. So product rule is giving us this answer. Now I'm going to write the same problem as x over e to the x and use the quotient rule to solve it. So remember, we first square the denominator, and then we copy the denominator here times the derivative of the numerator minus copy the numerator, which is x, and then times the derivative of e to the x is e to the x. We can factor out e to the x. You see that we are getting 1 minus x, which is awesome. And then e to the x squared means e to the x times e to the x. So 1 into the x will cancel, and you have the same answer. So it's awesome. What a great question. So we see that both methods can be done. So now, interesting. So these are the basics, right? We did the basics. We understand the basics of how it's done. And technically, I think that will be it. I would like to present one of the spicier examples, just because this stuff is eventually going to come up, and application is the most important part if you are dealing with applied mathematics. Obviously, you want to make sure that mathematics is used for physics, for chemistry, for engineering, all of these branches, including economics and business and everything else. So medical field. So talking about population, which concerns biology and environmental sciences and everything else, we know that there is that model for population which is not that good, but it's okay in the short term, which says that well, y is equal. Let's go. P of t, which is population of time, is initial population e to the kt. So this is something that you covered in your pre-calculus course, and this particular model is linked to the exponential function graph. But here you see that if we are talking about population of Earth, for instance, or anything else, as the time goes to infinity, which means as time goes on, the population goes to infinity. And we know that can't be, because the planet would have a finite surface area, finite resources in terms of energy and food and so on. So this model is not good on a long run. It's okay for short and close calculations. So if you are trying to find a better population model, you will have to use, also presented in pre-calculus 1, something is called logistics growth. And that one has a little bit scarier formula. So P of t. And I'm going to actually use an example from textbook to show this. Now, this one is very good because of the fact that it's logistics growth, which means it involves what we call carrying capacity, which is the horizontal asymptote that the function will approach but will never cross. That carrying capacity, depending on which paper you read, for our planet in terms of humans, is anywhere from 10 billion to 15.2 billion, I believe. And that is based on such a wide range, based on the amount of food and resources, land and so on, that it's around. So we are currently at 7.33 billion, and if 10 billion is the upper cap for human population, so that we can still get food and resources for everyone who's alive, That would be in the next 15-ish years, right? We would reach that carrying capacity of the planet at the way the population progresses right now. So these calculations are very important because they tell us the future. Now, when you take the derivative, and you remember that I told you derivative is measuring the rate of change, if I find the derivative of this population equation, I will find the derivative function which can compute what is the rate of change of population at any given time, which is a good value to know. So we are only learning here. We're going to have these application problems coming up. So over here, we are focusing only on figuring out what is the derivative of this. So you are looking at the quotient rule in this case, even though you should be doing the chain rule later on, but let's focus on the quotient rule now. So you have this denominator squared. You copy it in the numerator times the derivative of the top, which is 0, minus copy 800 times the derivative of the one in denominator. So derivative 1 is 0, so we just ignore that. But then you have 7 times negative 0.2, so it's negative 1.4 e to the negative 0.2t. So the whole first term drops because of it's times 0. We have a negative times negative is positive. So population at any time t is going to be so 83. So that's what, 122? No, 112. And then 1 decimal place. Like this. E to the negative 0.2t, 1 plus 7e to the negative 0.2t.
Bottom square?
Yes, it is. Please pay attention. Thank you.
Is it necessary to drop the top e down so it has a positive exponent?
No, it's not. When you can, you do it. The one from the bottom cannot be taken up to the top because of 1 plus, but this e to the negative definitely can go down. Sense the tone of the line. So, derivative function generates all of the slopes of tangent lines which measure the change along the function. One more time. The derivative function generates / computes all of the slopes of tangent lines which measures the change along the function. That is something that was defined in 3.1, and that is something that will not leave us ever. The purpose of the existence of derivative in this world is to measure the change, and that is accomplished by figuring out the slope of the tangent line at the point you want to measure. So velocity is a derivative of position function. Acceleration is the derivative of velocity. These concepts, in terms of the derivative, are all linked by the fact that you are looking for the slope of the tangent line at every point along the function, and you want to measure how much the function changes at that point. So no matter what you learn in terms of the rules and properties and formulas for derivatives, the main problem and the main focus stays on calculating tangent lines, calculating the slope of the tangent line and then figuring out what is the tangent line. So just a little bit of the importance of the tangent line is that you can calculate trajectories, you can calculate the velocities, acceleration, you can calculate a lot of things because they measure the change. And then for business, you're talking about marginal cost and marginal profit. Again, it is the change in the original profit equation, original cost equation, and so on. So now going to our course and chapter 3 and 4 and so on, we learned that the derivative of, let's say, x cubed is 3x squared. We know that what we memorized through that formula n to the x to the n minus 1, we memorized that so that we don't have to do this every time we are supposed to find the derivative. Right, so this was the way you were supposed to do it. Foil that thing 3 times, minus x cubed, and then do the rest of the magic. You will eventually end up with 3x squared. So what we learned today so far with the product rule, quotient rule, and all the other rules we learned the shortcut method so that we can avoid taking these limits every time we need the derivative. Now, the purpose of figuring out derivatives, I already said that, is to measure the slopes of the tangent lines. And we are going to actually find those tangent lines for whatever concept we cover. So you learn the derivative of sine is cosine y because you will actually have to find the tangent line. X cubed, eventually find the tangent line. So all of these things, including product rule, quotient rule, chain rule, the implicit differentiation that is coming up, logarithmic differentiation is coming up, all of these different ways of figuring out derivatives for different situations, that's all mechanics. The main problem of calculus 1 is figuring out the equation of tangent line. One more time, the main problem and the main focus of calculus 1 differentiation portion is to figure out the slope of the tangent line. So now, we are going to take a look at the tangent line problems. And we are going to understand that this one never goes away. Calc 1, Calc 2, Calc 3, differential equations, this is one of the main and focus points of all of the calculus. And we learn it obviously in Calc 1. So the procedure is that given function f of x and a point x, well actually a, f of a, we can find equation of the tangent line to the f of x at x equals a. Those are the words. Here is the picture. So this red line is called tangent line. Remember, I said it kisses the function, which means it touches the function at exactly one point, and one point only. That point is at x equals a, and that point has the coordinates a, f of a. So now we are going to take a look at this procedure. The procedure goes like this. We have f of x given. We find f prime of x. We compute m equals f prime at a. And I'm going to actually use the little arrow here and say plug in a. So f prime of x is the derivative function, and as soon as you plug the value that you're looking for, the derivative, that you're looking the tangent line for, it immediately becomes a slope. And then we use y equals mx plus b to find b. We have tangent line. So this is the procedure how to find tangent lines right here. So we have f of x given to us, and it's also a. A is given to us. We find the first derivative, plug a into first derivative to get the slope. Then you have a and f of a, those are your x and y, and you have m. Plug all of that in y equal mx plus b, it will give you b, and then you have m and b, which is needed to compile the line. So let's do the example, starting something simple, and then we'll take a look at the spicier examples later. So let's say f of x is equal to 2x cubed minus 1 at the point, I don't know, 2, let's go with 2, and we can compute, let's just say x equals 2. Now, that's your a, all right, because x is equal to a. X is equals to a, x equals to 2, so that's a is 2. So what's the procedure? We first find the derivative, which is 6x squared. From there and there, we write that m is equal to f prime at 2, which is 6 times 2 squared, which is 24. Are we all good on this so far? So find the derivative and then plug a into that derivative to find the slope. So now you have that m is 24. We also have that x is 2. We need to find the f of x, which is y. So f of 2 is y, which is, well, let's put y equals f of 2, which is 2 times 2 cubed minus 1, which is 15. So now we have that y is 15. So y equal mx plus b. We have 2 and 15, and we have that m is 24. Plug everything in. 15 is equal to 24 times 2 plus b. 15 minus 48 is b. So b is equal to negative 33. So the tangent line at 215 is y equals 24x minus 33. It is a linear line, straight line, and that line goes through 215. And you can see that, right? 2 times 24 is 48. 48 minus 33 is 15. So the tangent line goes through that point, and the function goes through that point. So, and that's the point where they touch each other. Now, here is the power of Mathematica and how it can help you with your education. If you really want to understand this stuff, what you do is you graph the answer to understand it better. What it means, the tangent line, and all of that stuff. So you go to Wolfram Alpha query, and you simply say graph, you type the first function, then you type word and, type the second function, and it will draw both of them at the same time, and you will see that they touch exactly at 215. So I'm going to say graph, and what were the functions? 2x cubed minus 1. So graph 2x cubed minus 1 and 24x minus 33. 24x minus 33. Oops. 24x, there we go, minus 33. It will graph both of them on the same viewing window. And we do not see intersection yet, so we'll first make it larger, and then we'll there we go. So if you look at the intersection point of these two, 2.0, that's not 20, that's 2.0. So 2, and here's 15. So that's what I mean. The blue line is the function, and the orange line is the tangent line. Now, this is a very useful tool. If you are working on homework, the question says find the tangent line. You finish the whole thing, and all you need to do is to type it in. And as you see, I did not talk about any special computer language or anything like that. I wrote what I say. Graph 2x cubed minus 1 and 24x minus. I didn't even say y equals, because the computer is going to pick that up. It's programmed that way. So just don't be lazy, right? If you care about this stuff, you want to learn it, all you need to do is to type it in and check, and then with that, the greater understanding will come along. So now, as I mentioned, do we get to find the tangent lines with the product rule? The answer is hell yes, because product rule is a way of taking the derivative. As long as you're taking the derivative, you are looking for tangent lines. So whether it's basic derivative, chain rule, product rule, quotient rule, implicit differentiation, all of them are methods to take derivatives, which means, yes, we are looking for tangent lines. So you could have a product rule involved. So next example, function f of x is given as, let's say, 4x e to the x. And we want to find the tangent line at 0. So that 0 is your a. We find the derivative, and here is where the product rule happens. So copy the first one, 4x times derivative of the second, which is e to the x, plus copy e to the x times derivative of 4x is just 4. We factor out 4e to the x, and we are left with x plus 1. So we have x plus 1. This is our derivative. And we go on with the procedure for the slope of the tangent line, which is m is equal to the first derivative computed at a, which is in our case 0. We get 4 times e to the 0, open parenthesis 0 plus 1, and the whole thing is just 4. Because e to the 0 is 1, 0 plus 1 is 1, 4 times 1 times 1 is 4. So we have the slope. Now, we have the x is 0. What is y? How much is y? 0. It's 4 times 0 times e to the 0, which is 4 times 0 times 1, 0. So what do we have? Now we have that slope is 4 and the point is 0, 0. It goes through the origin. So what's the equation of the line? Y equals 4x. Very good. Y equals 4x. And that is the tangent line at 0, 0. Now, since this is a curve, that is going to change. The line is going to change as you go from one point on the graph to another, because the slope changes, right? The derivative stays the same, but computing at a different x values is giving different numbers on the other end, which will obviously immediately change the equation of the tangent line. Because once m changes, all of the other calculations change. So problem of a tangent line stays the focus of calculus 1, regardless of what type of derivative we take, what rule we learn. The tangent line problem is the problem that we are solving throughout. So I show you the tangent line problem with something that we covered in 3.1 or 3.3, and now from 3.4 we have the product rule. Again, product rule is just a way to take the derivative. The tangent line problem stays the tangent line problem throughout. Good. Do we have the second order derivative, third derivative? The answer is yes, and they exponentially become more annoying to take because the expressions keep growing, right? Every time you take a product rule, you start with one term, you end up with two terms on the other side, and then at least one of them or both will have the product rule again. So as you keep taking these second and a third and a fourth derivative, they might expand even into more. Good. That is it on product and quotient rules. You will have to learn those formulas. That's the part of the knowledge that is required for Calc 1, and that will be on all of our tests, including the final. These are important formulas and important concepts and shortcuts, so we don't have to bother with the limit and algebra there. I'm going to stop the stream, take, what, 2 minutes, let's say, off, and then we'll